Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Astronomical observation has taught us almost everything we know about the universe around us. Soon, the James Webb Space Telescope will finally be ready to deploy in space. If it survives to orbit, we will see farther and more clearly than ever before. Let's discuss how this amazing technology works and how it will finally get to space. The James Webb Space Telescope is a joint project between the United States, Canada, and Europe. NASA built the telescope itself. The Canadian Space Agency built much of the instrumentation, and the European Space Agency will be providing transportation. The James Webb is meant to replace the aging Hubble Space Telescope. Here we can see the Hubble and James Webb relative to their size. The Hubble was launched in 1990 on Space Shuttle Discovery. After an extra shuttle mission to correct a lens problem, Hubble began sending humanity an amazing collection of images. These have been the clearest images of deep space we have. The Hubble has lasted over 30 years, but its time is drawing to a close. Why do we need telescopes in orbit when we can build much bigger ones on the ground? The reason is that light is absorbed, distorted, and scattered by atmospheric dust and gas. Some wavelengths of light don't make it through to the Earth's surface at all. Last lesson, we discussed the absorption of photons by the Earth's atmosphere. Here you can see what gets absorbed. It turns out that the best way to view distant star systems is in infrared, starting here. Since most of this is absorbed in the atmosphere, no telescope on Earth can see in these wavelengths. The Hubble Space Telescope is able to see just a little into this range. Here are images as seen with visible light, and here are the same as seen in infrared. Hubble can also see a little into ultraviolet. This wavelength is also not available on Earth. In order for our telescopes to see in these wavelengths, they have to get above the atmosphere. Here are some telescopes that we have put into orbit. There are telescopes like Hubble, X-ray telescopes like the Rossi X-ray Timing Explorer. This can see white dwarfs, neutron stars, and black holes. And gamma-ray telescopes like the Swift, dedicated to studying these mysterious gamma-ray bursts. And the Wilkinson Microwave Anisotropy Probe, which helps us see back to the energy at the beginning of time, when our universe started in the Big Bang. All of these give us unique data about the universe, but if you look at the available wavelengths, you will see that we are blind to a large part of the spectrum. The James Webb will give us sight in these regions. Infrared vision in space is important for several reasons. The universe has been expanding since it started 13.8 billion years ago. The rate of expansion is still being debated, but data from the Hubble Space Telescope is helping us understand these factors. Matter itself cannot be accelerated beyond the speed of light. But space-time does not have that limitation, and the edges of the universe have moved far away from us, many times faster than the speed of light. And this space-time has carried with it the light from the earliest stars. No matter where we live in the universe, the farther we look into space, the farther back we are seeing in time. But the farther back we see, the faster these ancient objects appear to be moving away relative to us. Think of dots on an expanding balloon. Every dot sees every other dot moving away from it. An ant living on a spherical balloon would find no edge. And if the balloon expanded faster than the ant could walk, the balloon would effectively, to the ant, be infinite. This means that light from the early universe is moving away from us and is therefore redshifted. The further away we look from our relative position, the more the light has shifted out of the visible spectrum. Some of the earliest light has shifted all the way into the microwave region. This is called the cosmic microwave background radiation. And here are the images we have collected from this wavelength. But to see the earliest stars, we need to see in these wavelengths. And to see clearly, we need to collect a lot of photons. That requires a big mirror. More surface area equals more photons. And the James Webb Space Telescope is specifically designed to see infrared light. Here is the spectrum that it can detect. The James Webb has a 6.5 meter in diameter gold-coated beryllium primary mirror, divided into 18 segments, with a secondary mirror to gather light from the primary and focus it on the imaging system. This is much larger than Hubble. The mirror is too big for any existing operational rocket, and the sides or wings have to be folded back to fit into a fairing. Here you can see it folded, making it less than 5 meters wide. And here you see the wings deployed. This will give the full diameter of 6.5 meters. Folded, the satellite will be able to fit into the Ariane 5, as you see here. The mirror is mounted on a tower and satellite bus. The satellite bus supplies propulsion, navigation, power, and communications for the satellite. When we unfold the wings on Earth, we must offload some of the weight. In space, the satellite will have mass, but no weight. Here we see the satellite leaving Earth orbit. As it moves away from the Earth, it will deploy a solar panel for energy. This includes the Science Instrument Module and star trackers made by Canada. Along the way, it will make course corrections as needed and continue toward its destination, which is the Earth-Sun Lagrange Point 2. And deploy a communications antenna, so it can communicate with the Deep Space Network. It will make more orbital adjustments as it climbs higher. Then the forward sunshield will deploy, and the aft sunshield. The tower will extend upward. Once deployed in space, a sunshade will be deployed, as you can see. These are multiple layers of material with low thermal conductivity. And once both mid-booms are deployed, the membranes are stretched, making room for the thermal membranes to be spaced out, allowing thermal isolation. This is a momentum management flap. It helps balance the solar pressure on the shield. The satellite will keep the sun shield pointing toward the sun. Now the wings will be deployed and use a cryocooler to keep the mirror at a very low temperature. Here you see the aft radiator deployed. We need somewhere to reject the heat pumped from the mirror. At this point, the cryocooler starts to lower the mirror's temperature. The mirror must be kept at or below 50 Kelvin. Since the mirror is made to reflect infrared, too much heat in the mirror itself would interfere with imaging. Cryocoolers are usually Stirling engines, and the system will continue on its way to L2. It will then start to orbit L2. Construction on the James Webb was started in 1996, and a launch was initially planned for 2007, with a budget of $500 million. But the project had numerous delays, and a full redesign was needed in 2005. This was completed in 2016. And testing was complete in 2018. The James Webb was supposed to launch in June of 2018, but was delayed for further testing. Then in March of 2020, the pandemic hit, adding further delays. The total cost is now almost $10 billion. The James Webb was then scheduled to launch on Halloween, 31 October 2021. But scheduling problems with the launch vehicle has delayed things until 18 December of 2021. If all goes well, the James Webb will launch on an Ariane 5 from Kourou, French Guiana. Interestingly, this tiny country in South America is considered part of the European Union. Europeans first arrived here with Christopher Columbus just before the year 1500, though Amerindian peoples had settlements here going back at least 12,000 years before that. After a long history, French Guiana became a French territory, and then a part of the French Republic, and therefore the European Union, in 1946. Continental Europe does not have a good rocket launch site to maximize the boost from the Earth's spin. You need to launch to the east from near the equator. France had launched its first satellite, the Asterisk A1, into orbit from Algeria, aboard a Diamant A rocket in 1965. The Diamant was a 3-stage hypergolic rocket, up to 23.5 meters tall with a diameter of 1.34 meters, had a mass of 18,400 kilograms, and could get 160 kilograms to low Earth orbit. That same year, construction of the Space Center in Kourou was begun. At that time, Europe was determined to compete in the space race. The British had been developing several rocket systems, including the Blue Streak and Black Arrow. But after successfully placing a satellite into orbit from its Woomera launch site in Australia, the British stopped development of its own rockets, the only nation to ever do this, depending on its allies to launch satellites for it. The French were determined that Europe would maintain an independent access to space, and started launching rockets from Kourou. They took over development of the Blue Streak, and over time it became the Europa rocket system. The Europa rocket was a 3 to 4 stage system, with an RP-1 kerosene-powered first stage, a hypergolic second and third stage, and sometimes a solid propellant fourth stage. The Europa was 33 meters tall and about 3 meters in diameter. It had a mass of 104,670 kilograms, and could get up to 1,440 kilograms to low Earth orbit. In 1973, it was agreed that the French, with the help of Germany and the United Kingdom, would develop a more advanced rocket system. This system would be called Ariane. The Ariane 1 was a 3-stage rocket system. The first 2 stages were hypergolic, using unsymmetric dimethylhydrazine and nitrogen tetroxide, while the third stage was liquid hydrogen. It was 50 meters tall, with a mass of 207,200 kilograms, and could get 4,850 kilograms to low Earth orbit. You will notice over here that the percentage of mass to orbit is increasing. This is an excellent measure of a rocket system's overall efficiency. Ariane 2, 3, and 4 were larger versions of Ariane 1, also using hypergolics and hydrogen. Then came Ariane 5. Ariane 5 is a total departure from the previous European rockets. Ariane 5 had a hydrogen-powered core stage with new Vulcain engines, also using massive solid propellant boosters, and in this way is most similar to the larger American Space Launch System, the main difference being that the Ariane 5 actually launches. The Ariane 5 has used hypergolic second stages, but also has a hydrogen-fueled one. It has a maximum mass of about 770,000 kilograms, and can get up to 20,000 kilograms to low Earth orbit. The James Webb Space Telescope has a mass of 6,500 kilograms, but the extra delta V is needed to go not to low Earth orbit, but to its final destination at L2. The Hubble is orbiting the Earth at an altitude of about 540 kilometers. The James Webb will orbit in L2 with a perigee of 374,000 kilometers and an apogee of 1,500,000 kilometers, with a period of 6 months. The Ariane 5 also has a very large payload volume. At 5 meters diameter, it is equal to a Falcon 9. But at almost 4 meters taller, it has 40% more volume. But the Ariane 5 is not the only rocket capable of launching the James Webb Space Telescope. There were in fact several other options available. Here you can see a comparison of usable payload volume across several launch platforms. The artist has used a humpback whale to demonstrate relative size. The Delta IV and Atlas V rockets have an even larger volume, though most of the Atlas V is taken up by the Centaur second stage. But it still has more usable space than the Ariane 5. Both the Delta IV and Atlas V could have accomplished this mission, and they appear to have a higher success rate than the Ariane 5. The Ariane 5 has in fact been very reliable over the last almost 2 decades. with only one partial failure over 96 launches. The last failure was in 2002. But why does the mirror of the James Webb need to be so large? The larger the primary mirror of a telescope, the more photons it can collect. That gives the final image a higher resolution. In short, we can see more clearly, all things being equal, with a larger mirror. The equation for calculating the resolution of an imaging system is theta equals 1.22 times the wavelength of light collected divided by the diameter of the mirror. Let's start with the human eye. Though it's not a reflective system, it can still give us a good comparison. The average human retina is 32 millimeters across, but the pupil limits photon collection and is about 7 millimeters or 0.007 meters across. Human vision is invisible light, of course. The limit of the visible light spectrum is violet, with a wavelength of 380 nanometers. That's 0.00000038 meters. If we put that into our equation, we get a resolution of 6.6 times 10 to the minus 5, or 0.000066. The Hubble Space Telescope can see into ultraviolet, down to 100 nanometers in fact. This gives it a resolution of 5.1 times 10 to the minus 8. The Hubble Space Telescope can see 1,303 times the resolution of the human eye. The James Webb Space Telescope can see in an area where we are currently blind, starting at 600 nanometers and going out to 28,400. At this smallest wavelength, the James Webb will have a resolution of 1.1 times 10 to the minus 7. That's 588 times as good as the human eye, but a lower resolution than Hubble. Despite the greater size of the James Webb mirror, the longer wavelength reduces the resolution. But again, this is a wavelength that we are blind in. Half as good as Hubble should let us see the beginnings of time with incredible clarity. What else can we do with infrared telescopes? Stars put out a lot of light. Most of this is in the visible spectrum, as you see here. For example, our sun puts out 3.86 times 10 to the 26 watts of energy. The spectrum of a star is determined by its temperature. This is a spectrum for stars in general. And here is the spectrum of our sun. If we compare the radiance of this energy to the wavelength, we can clearly see that most of the sun's energy output is in the visible spectrum, with much less in the infrared. The visible light put out by most stars completely overpowers any light from a planet orbiting that star. Planets don't generate much visible light. They reflect the light from the star they orbit. This is called planet shine. When you see a new moon in the sky, you are seeing Earth shine reflected onto the moon. Reflected light is measured by a factor called albedo. Albedo is a measure of the diffuse reflection of light from the total that strikes an object. It is a measure of emitted versus absorbed or scattered light. This is reported as a fraction. The light that hits is valued at 1.0. The fraction reflected will therefore be between 1.0 and 0.0. A perfectly reflective metal surface would be 1.0, and a perfectly absorptive one, 0.0. But it gets more complicated. Albedo can be measured in one wavelength or all wavelengths. Monochromatic albedo is just one wavelength. And there are two other metrics of albedo. One is called bond albedo and the other is geometric. The bond albedo is the ratio of the total flux reflected and scattered in all directions. The geometric albedo is the ratio of the total flux reflected back in one direction, relative to a reference surface. This reference surface is a perfect reflector, with a bond albedo of 1.0, reflecting in all directions equally. If a surface preferentially reflects light in a certain direction, then it can reflect a higher ratio of light than the idealized surface. If the light source is in the same direction as your detector, think of it like a concave mirror. You send a light beam out with a certain measure of brightness, and the light coming back may be brighter at your point of measurement than the light you sent out. This can happen if the surface is made of angular particles instead of smooth round ones, or depending on atmospheric properties. Think of geometric albedo as a person's ability to observe the reflected light from a specific vantage point, a kind of retroreflection. Rules of thumb. Bond albedo is always between 0 and 1. Geometric albedo can be more than 1. Therefore, bond albedo may be greater or less than geometric albedo, depending upon the properties of the surface and atmosphere of the body. The albedo of Mars is usually reported as 0.15. This is the geometric albedo. Most albedos are reported as geometric. Here you see the bond and geometric albedo of different planets in our solar system. Overall, Mars reflects 25% of the light that strikes its surface. But from our vantage point on Earth, we only see 15% reflected of the total. The Earth has a bond albedo of 0.306 and a geometric albedo of 0.367. That means it reflects about 31% of the overall sunlight shining on it, but reflects back towards the sun 37% of what an idealized surface would reflect. This is the opposite of Mars. On Mars, the bond albedo is higher than the geometric. On Earth, the geometric albedo is higher than the bond. If the Earth was completely covered in ice, as it has been in the past, it would have an albedo of around 0.84, meaning it would reflect about 84% of the light from the sun that struck the Earth. If the Earth was completely covered in forest, it would reflect only 14%, giving an albedo of 0.14. The albedo of an exoplanet or asteroid can tell us something about the physical properties of that object. And some asteroids are blacker than coal, absorbing almost all visible light. If we look back at the spectrum of the sun, we can see that it puts out much less energy in the infrared. A planet, on the other hand, will usually retain and even generate heat from atmospheric effects and nuclear decay. This will make it brighter in the infrared than it might be in visible light relative to the star it orbits. This means that an infrared telescope in orbit would have a much better chance of distinguishing a planet in another solar system than a visible light telescope. Our best chance of seeing alien worlds is with an infrared telescope. Let's hope the James Webb Space Telescope makes it safely to orbit. But what if it does not? Would it take another $10 billion and 2 decades to try again? No, we have a better option on the horizon. Consider this. The size of an orbital telescope is limited by the size of the rocket carrying it to space. This is the payload volume of Starship when compared to other rocket systems. If we took a Starship and made the entire top cone a folding space telescope mirror, we could launch it into orbit and open it up, giving us a telescope diameter of about 49 meters. If we use the same mirror technology as the James Webb in a Starship infrared observatory, the larger mirror size would give us a resolution 4,433 times that of the human eye, 7.5 times better than that of the James Webb, and 3.4 times better than the resolution of Hubble. Not only might this let us see alien worlds, but in the coldest, darkest regions of space, planet killers are orbiting mercilessly in the Oort cloud, waiting for a chance impact to send them on a collision course with the Earth. But no matter how black their surface, asteroids emit infrared light. A Starship orbiting infrared observing telescope would be our best defense against the most devastating catastrophe the Earth has ever seen. Something to think about. Thanks for listening. Please don't forget to like and subscribe, and stay safe at Astra Pro Terra.